Hello, this is the fifth lecture of this course on interpreting ABGs, and I'm Eric Strong from the Palo Alto Veterans Hospital and Stanford University. Today I will be discussing the anion gap and how it is used to classify different types of metabolic acidoses. The learning objectives are as follows. First, to understand the origin of the anion gap. Next, to be able to list the major factors that affect the anion gap, including how to correct the anion gap for hypoalbuminemia. Finally, to be able to distinguish an elevated anion gap metabolic acidosis from a normal anion gap metabolic acidosis. Measurement of the anion gap is a critical step in approaching the differential diagnosis of a metabolic acidosis. An elevated anion gap indicates the presence of a non-routinely measured anion, which is usually caused by the production of a pathologic acid. Let's take a closer look at exactly what the anion gap is. In the body, the concentration of cations needs to equal the concentration of anions in order for us to be electrically neutral. More exactly, the concentration of positive charge needs to equal the concentration of negative charge. In the serum, the vast majority of positive charge is carried by the sodium ions. A concentration of 140 milliequivalents per liter is typical. Potassium ions have a small but easily measured concentration, usually about 4. Then there are a number of cations which are less frequently or less easily measured. These include calcium, magnesium, and various positively charged proteins. Negative charge in the serum is largely carried by chloride and bicarbonate. Here are some typical values for those ions. In addition, there are ions that are less frequently or less easily measured. They include phosphates, sulfates, and negatively charged proteins. As you can see, the amount of unmeasured anions just happens to exceed the amount of unmeasured cations. This difference between the two is the anion gap. As you can see from the diagram, potassium is usually lumped together with the unmeasured cations, despite it always being measured concurrently with sodium. I suspect this is because the absolute value by which potassium can vary between patients is so small that it has negligible impact in the anion gap assessment. Mathematically, we can say that the anion gap is equal to the unmeasured anions minus the unmeasured cations, including potassium. This is equivalent to sodium minus the sum of chloride and bicarbonate. The normal range for the anion gap is approximately 8 to 12 milliequivalents per liter, but is lab specific, and you should really check with your own lab for its normal range before drawing conclusions about a patient's acid-base status. For purposes of the remaining lectures in this course, I will assume that the upper limit of normal is 12. An uncommon alternative to the above calculation is to include potassium. Thus, the anion gap is equal to the sum of the sodium and potassium minus the sum of the chloride and bicarb. Using this alternative, one would expect the normal range to be closer to 12 to 16. Let's see a graphical representation of the electrolyte differences in normal gap and elevated gap metabolic acidoses. First, here is our normal acid-base status, with some normal values of commonly measured cations and anions. This demonstrates a normal anion gap of 12, which is 140 minus 24 minus 104. In a normal gap metabolic acidosis, bicarbonate concentration is decreased and chloride is increased in roughly a 1-to-1 ratio. This can be seen with either loss of bicarbonate or decreased excretion of acid by the kidneys. As you can see, there is no change in the value of the sodium minus bicarb minus chloride. Thus, the anion gap is unchanged. Due to the fact that chloride is increased, a commonly used synonym for a normal gap metabolic acidosis is hyperchloremic metabolic acidosis. In an elevated gap metabolic acidosis, there is usually excess production of a pathologic acid, which becomes an unmeasured anion when it dissociates and is buffered by bicarbonate. The bicarb is thus lowered, but chloride is not increased in response, so the anion gap is elevated. The only cause of an elevated gap acidosis not caused by excessive production of a pathologic acid is severe renal failure, in which the kidneys are no longer able to normally excrete phosphate and sulfate, leading to their accumulation in the blood and which contribute to the concentration of unmeasured anions. I will discuss the differential diagnosis of both normal gap and elevated gap metabolic acidoses in more detail in later lectures. However, I'll quickly run through the list to give you an idea of how assessment of the anion gap can assist with determining possible diagnoses. A normal gap metabolic acidosis can be due to either the loss of bicarbonate or due to decreased renal hydrogen excretion. The former can be due to diarrhea or various forms of GI drainage, type 2 renal tubular acidosis, the carbonic anhydrase inhibitor acetazolamide, and as a chronic complication of ureteral diversion surgery. Decreased renal excretion of hydrogen can be seen in renal failure or either in type 1 or type 4 RTA, the latter being largely synonymous with hypoaldosteronism. Etiologies of an elevated gap acidosis are a bit more complex. You may recall this diagram from Lecture 2. I will save a detailed discussion of this for later, but very briefly, on the left are a variety of pathologic processes, and on the right are the unmeasured anions that accumulate and lead to the elevation of the anion gap. Here is the same information displayed slightly differently. First, lactic acidosis, as a consequence of numerous different processes, can lead to accumulation of lactate. Ketoacidosis from DKA, alcohol ingestion, or starvation leads to accumulation of acetoacetate and beta-hydroxybutyrate, which are collectively known as keto acids, though this is a bit of a misnomer as the latter is not actually a ketone. Methanol ingestion leads to formic acid, and ethylene glycol is metabolized into glycolic, glycoxylic, and oxalic acids. Toluene inhalation from sniffing glue, if evaluated very soon after the exposure, can lead to high levels of hippuric acid. Finally, the acidosis which usually accompanies renal failure is the only example of one which can have an elevated anion gap but without the production of a new pathologic acid. Rather, as just mentioned, in renal failure a deficiency in excretion of phosphates and sulfates occurs, which contributes to the amount of unmeasured anions. There are a number of pathologic states that can result in alterations in the anion gap that are completely unrelated to a metabolic acidosis. A high anion gap can be caused by metabolic alkalosis by a subtle secondary increase in albumin concentration, as well as an increase in the negative charge of each albumin molecule in the presence of higher pH. Phosphate is an unmeasured anion, which is not accounted for in the calculation of anion gap. Thus, severe hyperphosphatemia may cause a mild anion gap increase. Lastly, an anionic paraproteinemia could also do this, though this is rare as most paraproteins are either electrically neutral or of positive charge. A low anion gap is predominantly caused by low albumin, since albumin is one of the primary unmeasured anions. Other causes could theoretically include excessive concentrations of any cation, including potassium, calcium, magnesium, and even lithium. Bromism can lead to a falsely low anion gap, as some lab equipment registers bromide as chloride. This can be seen with therapeutic levels of pyridostigmine bromide sold under the brand name of Mestinon and used for myasthenia gravis. Finally, the presence of a cationic paraprotein, such as a monoclonal IgG in multiple myeloma, can also lead to a low anion gap. In fact, an unusually low anion gap, in the absence of an obvious electrolyte disturbance or hypoalbuminemia, may prompt an evaluation for multiple myeloma. As hypoalbuminemia is the most common cause of a low anion gap, a formula has been empirically developed in an attempt to adjust the anion gap to account for it. The equation for this is as follows. The adjusted anion gap in milliequivalents per liter equals the measured anion gap plus 2.5 times 4 minus the albumin as measured in grams per deciliter. The reason to adjust for hypoalbuminemia is to prevent missing mild anion gaps. For example, a patient found to have an anion gap of 14 might not initially alarm a treating physician. However, if that patient was found to have an albumin of 1.5, the expected anion gap would no longer be 12 milliequivalents per liter, but rather 6. Thus, instead of the patient's anion gap of 14 being 2 higher than the upper limit of normal, it is actually 8 higher than what would be expected, which would be more concerning. Another way to look for this issue would be to use this equation. So, for example, if the measured anion gap is 14, you would add 2.5 times 4 minus 1.5. This is approximately 20, which would more than likely trigger additional investigation. The adjusted anion gap essentially tells us what the anion gap would be if the patient had a normal albumin. In order to see how analysis of the anion gap works in practice, I'm going to go through 4 quick examples. Before that, however, I just want to quickly go over this notation, which is commonly employed on the wards in the United States, but with which you may not be familiar if just starting out or if practicing elsewhere in the world. Essentially, you take this specific pattern of lines and around it write the values of the basic metabolic panel. This is the arrangement of values that has become standard convention, and I will use this notation frequently throughout the remaining lectures. I will also follow US convention regarding units, so sodium, potassium, chloride, and bicarbonate will all be in milliequivalents per liter, while the urea, which we inexplicably call the BUN, creatinine, and glucose will all be in milligrams per deciliter. So here is example number 1. We have a pH of 7.32, a PCO2 of 28, and a bicarb of 14. Step number 1, as always, is to look at the pH. Here we immediately see this patient has an acidemia. Step number 2 is the check of the PCO2. Since the PCO2 is deranged in the same direction as the bicarb, the process is metabolic, and thus a metabolic acidosis. From the last lecture, you know that step number 3 is to evaluate compensation. For a metabolic acidosis, we use Winter's formula, which asks whether the measured PCO2 is approximately equal to 1.5 times the bicarb plus 8. 1.5 times 14 is 21, plus 8 is 29, so yes, the equation holds true. We conclude that we have appropriate compensation. From this lecture, we will now add in step number 4, which is to calculate the anion gap. The anion gap equals sodium minus the sum of chloride and bicarb. Plugging in our numbers of 140, 116, and 14, we calculate the anion gap to be 10 milliequivalents per liter. As we are not given an albumin, we will need to assume it is normal, and thus the anion gap does not need to be further adjusted. So we have an appropriately compensated metabolic acidosis with a normal anion gap, or stated more succinctly, a normal gap metabolic acidosis. Example number 2, pH 7.28, PCO2 24, bicarb 12. Step 1, the low pH tells us that this patient has an acidemia. As step 2, the concurrently low PCO2 tells us that it is a metabolic process and therefore a metabolic acidosis. For evaluating compensation, we use Winter's formula again. Does the PCO2 of 24 approximately equal 1.5 times 12 plus 8? And it's close enough to call good. Thus, compensation is appropriate. Our anion gap again is sodium minus the sum of chloride and bicarb. So 128 minus the sum of 94 and 12, which is 22. Thus, this patient has an elevated gap metabolic acidosis. For example number 3, let's try something a bit more complicated. This time we have a very brief clinical vignette. The patient is a 58-year-old man with diabetes and chronic kidney disease who presents with an abrupt onset of dyspnea 2 hours ago. His pH is 7.47 with a PCO2 of 20 and a bicarb of 14. The elevated pH tells us the patient is alkalemic. Since the PCO2 is deranged in the opposite direction as the pH, the process must be respiratory in origin. So this patient has a respiratory alkalosis. Next, evaluate compensation. The vignette strongly implies that the process is acute. Therefore, from our last lecture on compensation, we know that in acute respiratory alkalosis, the bicarb should be decreased by 2 milliequivalents per liter for every 10 millimeters of mercury the PCO2 is below 40. With a PCO2 of 20, we would expect the measured bicarb to be 20. Since it isn't, compensation isn't appropriate, and another disorder is present. As 14 is significantly lower than 20, and thus trending more towards acidemia, it implies the additional process is a metabolic acidosis. It's important to note that this metabolic acidosis just identified is not just compensation for the respiratory alkalosis that we first identified, but rather an independent primary acid-base disorder. For step number 4, let's calculate the anion gap. 135 minus the sum of 114 and 14 is 7. In summary then, this patient has a respiratory alkalosis and a normal gap metabolic acidosis. Here is our last example. A 48-year-old woman is found unconscious next to an empty pill bottle at home. Her pH is 7.09, PCO2 34, bicarb 10. Step 1, we have an acidemia. Step 2, the low PCO2 tells us that she has a metabolic acidosis. Step 3, for compensation, we once again use Winter's formula and ask if the PCO2 of 34 is approximately equal to 1.5 times the bicarb of 10 plus 8. It does not. Therefore, compensation is not appropriate. As the PCO2 is higher than expected and trending more towards an acidemia, the additional acid-base disorder is a respiratory acidosis. The anion gap in this case is 12 milliequivalents per liter, which at first looks normal. But let's not forget that now we are given an albumin, and that's not normal. Normal albumin is approximately 4 grams per deciliter, so we must adjust the anion gap for the hypoalbuminemia. The anion gap adjusted equals the anion gap measured plus 2.5 times the difference between 4 and the measured albumin. For this patient, this will be 12 plus 2.5 times 4 minus 2. Therefore, the adjusted anion gap is 17, and our final diagnosis is an elevated gap metabolic acidosis and a separate primary respiratory acidosis. So that's the anion gap and its basic role in diagnosing acid-base disorders. In the next lecture, I will discuss the anion gap a little further and specifically how it can be used to diagnose triple acid-base disorders.